Material properties aren't something you can change, right? Well, with the introduction of smart fluids, we bridge the gap between a liquid and a solid. The fluid we are interested in discussing today is magnetohydrological fluid, also known as MR fluid or MRF. It is a combination of water or oil with carbonyl iron particles. This fixture behind me can be seen in the characterizations of metals laboratory section, which is a first-year course required for mechanical engineering technology students and EMET students. The point of the fixture is to compare viscosities for multiple variations of MRF and over varying magnetic field strengths. This particular fixture was designed and created by myself due to my involvement with the metals class. The procedure of testing these fluids paired with the lab write-up helps to get the students understanding how the material works, as well as getting their mind started on possible applications of this fluid. My professor who I work under used to be very involved with MRF, specifically for the purpose of polishing optics. One thing that she told me that really stuck with me is that the only limiting factor for the applications of MRF is your imagination. Today, however, I will be discussing how the material works, how to use the fixture, and how to interpret the data collected. So, this is a schematic showing how under the magnetic field, which is represented as the orange lines, as you have a magnetic field, the iron particles line up through the magnetic field, stiffening the solution and increasing the viscosity. So how do you use the fixture? So here you can see is a syringe with a connector piece here, and you're able to tell how much volume of fluid you have. Okay? So in order to run the test, you need to take this piece off, which is your weight source. You load your syringe. And as I was saying, this fixture is designed to measure the viscosity over varying magnetic field strengths. So you might be asking where the magnets are. So the magnets are encapsulated in this sheet metal, which is non-magnetic material, aluminum. And the reason why I incorporated it in there was because before I built this fixture, I was messing around with these neodymium magnets, and I actually got my finger caught in between two, and when I went to get it off, it actually punctured my skin and just kind of ripped it, and I was starting to bleed. So I decided, since it's a first year class, might as well try to keep the kids safe, because freshmen. So in order to run the test, you take the top piece, you load it on here. Make sure this is in the piece right there. Okay, so now you can run the test. If you were to run the test though, you would be timing the time it takes from when you release it to the time it gets down here. Okay, so we'll show you. This is without magnetic field strength in there. Okay. All right. So you get the time there. Since it's an experiment, you would run the test about 3 times because scientists know that the more data you collect, the better the average you get. So we'll compare it to two magnets. Okay, so you just push your syringe back up. All right, now this is with 2 magnets and the same force. And you'd stop the time. All right, so you may be asking, how does this give you a comparable data? Well, it doesn't. So in order to get the comparable data, some things you need to know are how much fluid you're going to be forcing through the inner piece. You'll need to know the diameter of the plunger, because that changes the pressure of the fluid. You'll need to know the diameter of the piece that you're forcing it through, as well as the length. You also need to know the field strength. So, in conclusion, we talked about how MRF is a smart fluid and how under varying magnetic field strengths you can change viscosity of the fluid. We also talked about how to use the fixture and how to calculate the dynamic viscosity. The only thing holding you back for the applications of MRF is your imagination.